In this video, we're going to take a look at visible light rays, how light interacts with objects to give them color, and how our eyes are able to receive these rays and interpret them as vision. Visible light waves are just one of a number of groups of wavelengths that make up the electromagnetic spectrum. Electromagnetic waves are transverse waves in the electromagnetic field, meaning they oscillate within this field perpendicular to the direction of energy. Each ray of electromagnetic radiation, including visible light, carries energy in discrete massless particles known as photons. What we call the range of visible light is just one segment of the greater electromagnetic spectrum, which comprises all possible wavelengths of electromagnetic radiation, including radio waves, microwaves, infrared and ultraviolet light, X-rays and gamma rays. These are not different types of waves, but rather names given to different sections of the electromagnetic spectrum based on their respective applications, and the only difference is each segment's respective range of wavelengths. The range of visible light falls somewhere in the middle of the greater electromagnetic spectrum, from around 380 to 700 nanometers in wavelength, and is simply the segment of the spectrum that can typically be perceived by a human eye. The specific wavelength of a ray of visible light determines its perceived color. Waves with a greater wavelength appear closer to red as they approach the invisible wavelength of infrared, while waves with a lesser wavelength appear closer to blue or violet as they approach the wavelength of ultraviolet light. Every possible hue which humans can observe is represented by a unique wavelength somewhere in the visible spectrum. While the ray's wavelength determines the resulting light's hue when observed by the human eye, the wave's amplitude, or the maximum displacement of the wave from its center line, determines the intensity of the light, which we perceive as brightness. Higher amplitude in a visible light ray means a higher intensity of light, as the wave is able to carry more energy in the form of photons per wavelength. There are a number of basic behavioral properties of light that allow it to be observed by the human eye, but the important ones for the purpose of this video are reflection, absorption, and transmission. Note that these properties are not unique to visible light and are applicable for all forms of electromagnetic radiation. White light, such as that emitted by a light bulb or the sun, contains rays of all perceivable colors, which, when combined, appear as white. Each surface which is hit by a ray of light can reflect, absorb, or transmit that ray, and the same material will respond differently to different wavelengths of visible light, for instance by absorbing some colors while reflecting others. For example, an object which we perceive as green will reflect a lot of the green light that hits it while absorbing most other wavelengths, meaning the light reflected by the object back at our eyes will be mostly green, giving the object its perceived color. When a light source is present, the continuous emission and movement of light rays, being absorbed by, reflected off, and transmitted through surfaces on their way to our eyes, is what gives us humans our vision of the surrounding environment. So how does the human eye actually process these light waves and turn them into vision? Firstly, when a ray of visible light hits the surface of the eye, it is refracted by the outer layer, known as the cornea, and a clear inner lens to focus the ray towards the sensitive layer known as the retina at the back of the eye. At the center of the retina are approximately 6 million photoreceptor cells called cones. Cones are one of the two types of photoreceptors in the human eye and are responsible for the ability to see color, as well as process finer details in our vision, while cells known as rods make up the rest of the photoreceptors and enable vision in low light. There are three types of cone cells in the eye, with each being especially sensitive to one of the three primary colors, red, blue, and green. When visible rays of the same color hit these photoreceptors, the cells absorb the photons carried by the waves and transfer their energy into electric signals, which travel through the optic nerve to the brain. Similar to how digital screens use red, green, and blue pixels of varying brightnesses to approximate a large array of colors, any individual photoreceptor cannot directly communicate to the brain the exact wavelength of the ray which triggered it, but rather only the intensity of the input it received with respect to that cell's specific sensitivity. By measuring the ratios of these signals of intensity from the red, green, and blue sensitive cones in the eye, the brain can estimate the wavelength of incoming rays to interpret these signals as color vision.